this question, you're asked to calculate the integral of x squared plus 2x minus 1 divided by 2x cubed plus 3x squared minus 2x dx. So let's see, which case is this? First of all, pay attention here. This is the integral of f of x dx, which is written as a rational expression, px divided by qx. What is the degree of the denominator? The degree of qx is equal to 3, and the degree of the numerator, which is your px, is equal to 2. So obviously the degree of the denominator is more than the degree of the numerator, so there is no long division. If the degree of the denominator and numerator are the same, you have to do long division first. If the degree of the numerator is more than the degree of the denominator, you have to do the long division. So now let us break down the denominator into smaller pieces. We want to use the method of partial fractions. Let's see which case is this. We need to break down the denominator into smaller pieces. Let us try to factor the denominator. Your denominator qx is equal to 2x cubed plus 3x squared minus 2x. So obviously, first of all, you can factor out x. Factor x. So if you write x in front of parentheses 2x squared plus 3x minus 2, now you have a quadratic expression to work with. This is quadratic expression. This quadratic expression can be written as 2x minus 1 times x plus 2. You can use factoring, or basically you can use quadratic formula to find the roots of a quadratic equation and then rewrite this as a multiplication of two linear expressions. But please pay attention here. Here you have x times, so qx is written as x times 2x minus 1 times x plus 2, which is the product of distinct linear terms. So this is your case 1. This is your very first case when qx can be written as a1x plus b1 times a2x plus b2 times a sub kx plus b sub k, or as you can see, it is the product of qx is the product of distinct linear terms or expressions, to be more precise. So in that case, when you have the integral of f of x dx, which is the integral of px over qx dx, this can be broken down into the integral of a1, which is an unknown numerical value that we need to figure out, divided by a1x plus b1 plus a sub 2, another numerical value, which we need to figure out, a sub 2x plus b sub 2 plus a sub k divided by akx plus bk. Then we take the integral with respect to x. So this is our goal. Our qx is basically written as the multiplication of distinct linear expressions. So let us begin, everyone. Now that we factored out the denominator into multiplication of distinct linear expressions, we need to find the new numerators. So how are we going to do that? Remember your function. Here you have px divided by qx. So I'm going to take this one, copy it down, copy this guy down here. So we have everything we need. So this guy can be written as a sub 1 divided by, guys, it doesn't matter which quantity you're going to take first. We're going to start with x, 2x minus 1, or x plus 2. No one's stopping you. You can switch in between these. Plus a sub 2 divided by 2x minus 1 plus a sub 3 divided by x plus 2. We can apply the shortcut. In applying the shortcut, first make sure that you take the common denominator between these. So let me show you. Take common denominator. And set the numerators equal to each other. So what do you have? You have x squared plus 2x minus 1 on the left-hand side. And on the right-hand side, you have a sub 1 times whatever is left from its denominator, 2x minus 1 times x plus 2 plus a sub 2 times x plus 2 plus a sub 3 times x times 2x minus 1. Okay, now let us apply the shortcut. In applying the shortcut, what we can do here, we want to get rid of these terms one by one. If you set x equals to 0, see what happens. On the left-hand side, you have 0 squared plus 2 times 0 minus 1. And on the right-hand side, you get a1 times negative 1 times 2 plus a2 times 0 times 2 plus a3 times 0 times negative 1. So we are just applying the shortcut for each case separately. See what happens here. This guy is 0. This guy is 0. And on the left-hand side, you have just negative 1. Negative 1 is equal to negative 2a1. So if you divide by negative 2, a1 is equal to a half. We found a1. It is just a half. So with the same argument, we're going to plug in, for example, x equals to a half. Then we're going to plug in x equals to negative 2. So if x is equal to a half, see what happens here. You get 1/4 plus 2 times a half minus 1 equals to you have a1 times 1 minus 1, which is just 0, so you don't even have to plug that guy in here, plus a2 times a half plus 2, plus a3 times a half times 1 minus 1. But again, please note that here you end up with some zeros. This is just 0. This guy is also 0. On the left-hand side, we have, let's see, a fourth. This becomes just 0 as well. So you get 1 over 4 equals to, here you have a sub 2 times a half times 5 divided by 2. You can get rid of these denominators. So a sub 2 is equal to 1 over 5, 1/5. Very good. We only left with a sub 3. To find a sub 3, we're going to use x equals to negative 2. So when x is equal to negative 2, you get 4 plus 2 times negative 2 minus 1 equals to a sub 1 times, you have negative 4 minus 1, you have negative 2 plus 2, this is just 0, plus a sub 2 times negative 2 times negative 2 plus 2 plus a sub 3 times negative 2, and you get negative 4 minus 1. So again, here you end up with some zeros. We're happy about that. This is just 0. This guy is 0. We expect that this is 0. We're looking for a sub 3, all right? So you have negative 1 equals to, here you have negative 2 times negative 5, or 10 times a sub 3. So a sub 3 is equal to negative 1 over 10. Beautiful. So we found all of these missing coefficients. Now we can go back up and plug them into the partial fractions and take the integral. So let me take this one, copy it down here for you. So let us erase a1, a2, a3. a1 is equal to a half. a2 is equal to a fifth. And a3 is negative 1 divided by 10. Well, now you can take the integral of both sides. The integral on the left-hand side with respect to x is equal to the integral on the right-hand side with respect to x as well. But these integrals should be easy for you because these are all ln. The integral of du divided by u is ln of absolute value of u plus c. So the very first integral is a half ln of absolute value of x. The second integral, please pay attention here. If you take u to be 2x minus 1, du is equal to 2 dx. So dx is equal to du divided by 2. So you end up with a 10th, 1 over 10, ln of absolute value of 2x minus 1. Let me move this down here so you don't get this confused. And this is du, which is equal to 2 dx. Okay, and finally, the last one is negative 1 over 10, ln of absolute value of x plus 2 plus constant of integration. And you can leave your answer like this. So this is the use of partial fractions in taking the integral. From pre-calculus, we move to calculus and use partial fractions to calculate the integral of these types of rational expressions. So let us go up and summarize this. So here we wanted to take the integral of x squared plus 2x minus 1 divided by 2x cubed plus 3x squared minus 2x dx. This is basically px divided by qx. since the degree of the denominator is more than the degree of the numerator, there is no long division involved. Our goal is to try to break the denominator down into smaller portions or smaller pieces. When we try to factor out x, we ended up with a quadratic expression, which was easy to work with. The quadratic expression can be broken down into 2x minus 1 times x plus 2. So this is your denominator, x times 2x minus 1 times x plus 2, which is basically case 1. If you can break down the denominator into the multiplication of distinct linear expressions, then you can use partial fractions. The partial fractions are a1 over a1x plus b1, which is your first linear term, a2 divided by a2x plus b2, second linear term, plus the rest of them, and you have a sub k divided by akx plus bk, which is your last linear expression. Now that we factor out the denominator into multiplication of distinct linear expressions, we need to find these new numerators, a1, a2, a3, a4, and so on. What is a1? What is a2? And the rest of them. So x squared plus 2x minus 1 divided by 2x cubed plus 3x squared minus 2x is a1 over x plus a2 divided by 2x minus 1 plus a3 divided by x plus 2. Make sure to take the common denominator. Well, in that case, the denominators are the same and the numerators must be the same. The numerator on the left is the numerator that you see just right here. And the new numerator after taking the common denominator is this combination. We used the shortcuts. We plugged in different values for x based on the value that make the denominator 0. So if you set x equal to 0, you get a1 divided by 0. So when you plug in 0, you can find a1. 2x minus 1 is equal to 0 gives you x equals to a half. So you plug in a half to calculate a2. When you plug in -2, it means that after setting x plus 2 equal to 0, x is -2. It helps you to calculate a sub 3. Are we done yet? Of course not. We just found a1, a2, and a3. Now you just need to plug them into the partial fractions and use the method of integration of du divided by u, which is ln of absolute value of u. So this integral becomes the integral of a half divided by x, which is ln of absolute value of x times a half. The integral of 1/5 divided by 2x minus 1 using regular u sub gives you 1/10 ln of 2x minus 1. And finally, the integral of -1/10 divided by x plus 2 gives you -1/10 ln of absolute value of x plus 2. Don't forget the constant of integrations.